Hello, pre-calc honor students. Here we are with 10.3 at double angle and half angle formulas. First, I'll look at one of the applications of all these formulas, and that's in sound and music, and how we can represent the sound of the violin and all its overtones with a complicated trig equation like this, where you see many different kinds of multiples on the variable inside sine and cosine. And let's look at this model for overtones. And first of all, I got this from GeoGebra, where I set up some sliders on everything. As you can see, as I change some of these sliders, we can change the look of the whole periodic function. But notice they all do have a period. I can make the effects of the overtones less pronounced by taking some of these coefficients down. Notice? There you go. So, it's a lot of fun. I think this was at 0.4. Oopsie. 0.4. Yeah. Okay, back to the slide. We'll come back to this in a bit. What would you estimate for this period? First, let me give you some hints here. The separate periods are 4, 6, and 2. Remember that 2 pi divided by b, the coefficient on x, 2 pi divided by b gives you 6. 2 pi divided by pi gives you 2. Well, let's try and figure this out. And what I can do is use the slider on GeoGebra, another slider where I change the period. So we can take a look at increasing this. Here's my point A, which slides along like this. And now if I think 2 is the period, if I go 2 later, clearly that's not. How about 4? No, occasionally lines up, but not at every element in the domain. How about 6? No. Got to crank it all the way up to 12. There, 12. And now see, it now goes from peak to peak. These two peaks are not one full cycle, because you got this coming down like this again. So there it is. It's got a period of 12. Let's get back to the notes. And let's see if you guessed that. The period is 12 because that is the least common multiple of each of the periods of each term. So bravo. Okay, now some of the formulas we're going to learn here. The double angle formulas. Recall that the sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. Well, what if we do a substitution and replace beta with another alpha? So it's sine of alpha plus alpha. Then the betas become alphas. And then we say there's no difference between two alphas, so it's the sine of 2 alpha. Sine alpha cosine alpha plus sine alpha cosine alpha. So you get the sine of 2 alpha equals 2 sine alpha cosine alpha. There's our first double angle identity. That's the easy one. Now, what happens then when we start looking at cosine of alpha plus beta? Well, we use the same trick again. Replace beta with alpha. So we get cosine 2 alpha equals cosine squared minus sine squared. So there's your next one. Now these are all listed in the book too if you want to copy them out of page 383. Page 383 has a list of all the formulas. You are expected to memorize these. This next test is a no calculator test. You got to know your double and half angle formulas. Now the thing is though, with the cosine double angle, we've got this Pythagorean relationship and its variations, like sine squared alpha equals 1 minus cosine squared alpha, and cosine squared alpha equals 1 minus sine squared alpha. So if we sub that in, replace cosine squared with 1 minus sine squared, we get 1 minus 2 sine squared alpha. And if we sub in the other direction, replace sine squared with 1 minus cosine squared, we get 2 cosine squared alpha minus 1. So you got a couple more forms of the cosine of 2 alpha. Oopsie. Do be careful, though, that cosine 2 alpha and cosine squared alpha are not the same thing. They have similar formulas. This is the Pythagorean relationship. This comes from the Pythagorean idea that we had earlier. This is a double angle formula. Notice the difference. And sometimes kids get a little sloppy. The cosine squared drifts down and looks like a cosine 2 alpha. The parentheses aren't really usually required here. Cosine 2 alpha is considered to be the same thing as cosine 2 alpha. You should interpret that not as cosine of 2 times alpha, but when you see it written like cosine 2 alpha like that, Just assume it means the parentheses around there. So you're taking the cosine of that whole angle. So the tangent double angle formulas, same trick again. Replace beta with alpha. Tan alpha plus tan alpha over 1 minus tan alpha times tan alpha. So you get there one more formula. 2 tan alpha over 1 minus tan 2 alpha. Okay. Now, let's apply this. Example 1. If sine alpha equals 4/5 and alpha is in the first quadrant, find the sine of 2 alpha cosine 2 alpha tangent 2 alpha. So let's start with the sine 2 alpha. Sine 2 alpha will equal 2 sine alpha cosine alpha equals twice sine alpha is 4/5. Cosine alpha we're going to have to figure out from a diagram. We're going to have to say, okay, we've got the sine of alpha is 4/5 in the first quadrant, so r is 5, y is 4. There's your alpha. And from those two, we get this side is 3. So the cosine of alpha is 3/5. And that's how we figure that part out. So we get 12, 24, 25ths for the sine of alpha. Now for the cosine of 2 alpha, 24 25ths for the sine of 2 alpha. For the cosine of 2 alpha, you've got your choice. You could actually not have, just stick to the original information and go 1 minus 2 sine squared alpha. So in case we made a mistake there with cosine, you're not going to mess up here. Sine of alpha is 4/5, and you're going to square all that. So it's 1 minus 2 times 16 over 25. 1 minus 32 25ths is a negative 7 25ths for the cosine of 2 alpha. And then let's practice one more here with our tangent 2 alpha as 2 tan alpha over 1 minus tan squared alpha. We're going to have to get that from our two givens here. Sine over cosine, if the sine of alpha is 4/5, cosine is 3/5, tangent is 4/3. So tan alpha equals 4/3. And we can substitute that in then. 2 times 4/3 over 1 minus 4/3 squared. 8/3 all over 1 minus 16/9. So let's use our LCD concept in a compound fraction here of 9. Multiply the numerator and denominator by 9 to get 24 over 9 minus 16, or 24 over negative 7, negative 24/7. Now, at this point, I just wanted to show practice on using all the formulas. You could have said, hey, we got the sine of 2 alpha and the cosine 2 alpha. So we could have just said tan 2 alpha equals sine 2 alpha over cosine 2 alpha, and we had those two from the previous spots. Sine was 24 25ths, cosine was negative 7 25ths. And sure enough, there's your negative 24/7 again. In fact, are there some shortcuts here? Could we have started with cosine 2 alpha instead and just used the given information and gotten negative 7 25ths, and then used a 1 minus cosine squared 2 alpha to get sine 2 alpha? Well, again, that would lead you with the ambiguity of plus or minus. Now you might say here, well, we know the sign of all these because alpha is in quadrant 1, so 2 alpha is definitely in quadrant 2, or is it? You see, you don't quite know that. But you would know that 2 alpha would range from 0 to pi, in which case the sign would be the positive answer. So there's little tricks like that you can do with the range of the given information to help determine the sign on some of these things. Okay, now here's another example. Derive a formula for sine 4x in terms of functions of x. So you want to get this out here. You can't just float out. This is not multiplication here. We can't reassociate it. We have to think of it first as the sine of twice 2x and use the sine double angle identity. So that's 2 sine 2x cosine 2x. And then use the sine 2x again to say it's 2 sine x cosine x. And cosine 2x, you got your choice. Let's go with cosine squared x minus sine squared x. But you could do none of the other two and you'd have slightly different answers, and I would accept any of those. When you distribute all this then, you get 4 sine x cosine cubed x minus 4 sine cubed x cosine x. Now, let's say here's an alternate answer that I would have accepted at this step. You could have said, oh, I've got twice 2 sine x cosine x. And then said, oh, for cosine 2x, I'm going to go with 2 cosine squared x minus 1. So now I've got 8 sine x cosine cubed x minus 4 sine x cosine x. I would accept that answer too. These are fine. And there's a third one too if you take the other option. This is why we don't really talk about a quadrupling formulas for sine and cosine. Now, half angle formulas go in the other direction. To get the half angle formulas, we've got a clever substitution we do with the double angle formulas. Take the double angle formula we just developed, and now let alpha equal x over 2. So that means you get cosine twice x over 2 equals 1 minus 2 sine squared of x over 2. You might think, well, what's the point? Well, we got cosine x now equals 1 minus 2 sine squared x over 2. By solving this for sine of x over 2, we're going to get a formula for sine of x over 2 in terms of cosine. So there'll be a half angle formula for you. Yes?
Hi.
Hi. So here goes. Let's try this. We're going to try and solve this monster for a sine of x over 2. So let's put the 2 sine squared x over 2 on the left. And then subtract the cosine x from both sides. So we got the sine squared of x over 2 equals 1 minus cosine x all over 2. So the sine of x over 2 equals plus or minus the square root of 1 minus cosine x over 2. There you go. That's the sine one, and notice we have this ambiguity here. That's one of the pains with doing half angle formulas. Let's do it with cosine as well. But we pick the other cosine double angle identity, this one that relates cosine to cosine twice of itself. So, do the substitution, simplify it, and now let's solve this for, oh, I'm sorry, this should be solving for cosine of x over 2. So here we go. Let's add a 1 to both sides. 1 plus cosine x equals 2 cosine squared of x over 2. Divide both sides by 2. 1 plus cosine x over 2 equals cosine squared of x over 2. And now, oopsie, put it in the wrong spot. Wink. And now cosine squared of x over 2 equals 1 plus cosine x all over 2. So cosine of x over 2 equals plus or minus the square root of 1 plus cosine x over 2. Here's our cosine formula. Now recall that the sine one was very similar. Plus or minus the square root of 1 minus cosine x over 2. The way I keep these straight is I think of, on the unit circle, if I've got an angle x, and I cut it in half, and we're going to use this original cosine x of here. Notice they both involve cosine x. But one of these is bigger and one of these is smaller because you go 1 plus cosine is going to be bigger than 1 minus cosine in the first quadrant. So when you cut it in half like this is x, and then this is angle x over 2, this is x like this. Clearly the sine is getting smaller, and the cosine, how far over, that's getting bigger. So that's why the plus goes with the cosine. Now you might also say, well, why are both cosine and sine in terms of cosine x? Well, it has a lot to do with where we got them from. We got them from the double angle formula for the cosine, because the sine double angle formula involves both sine and cosine. How are you going to solve it for just one of them? So the backwards trick won't work. Similarly, it won't work on that one cosine double angle identity. That's why I don't use this one. If I make both these x over 2, then I got this as x. How do I get just 1 cosine of x over 2? So that's why we pick those two. Now example 3, find the exact value of cosine of 5 pi over 8. Well, first you got to recognize that this is half of 5 pi over 4. 5 pi over 4 divided by 2. So it's going to be plus or minus the square root of 1 cosine is add plus cosine 5 pi over 4 all over 2. So plus or minus the square root of 1 plus cosine 5 pi over 4, remember from our unit circle days, here's 5 pi over 4 cosine, that's the negative 1. So that's negative square root of 2 over 2 all over 2. Now I want to rationalize the inside there a little bit. Let's multiply this by 2 over 2. We're not going to get it totally rationalized. Well, maybe we will. Let's check this out. We get, now let's decide this plus or minus thing. 5 pi over 8 is actually in here, and the cosine of 5 pi over 8, judging from my unit circuit analysis, there will be the x-coordinate at the angle 5 pi over 8. That is definitely less than 0. So I want to use the negative form of this. Do you see how I made that decision? You've got to do that. If you got a variable, you can't, but in this case we have a specific angle we can look at and judge where its value should be. So it's negative 2 minus the square root of 2 all over 4. And now we can distribute the square root over the division, but go no further. That's it. 2 minus the square root of 2 all over 2. That's a messy answer, but we're going to accept it. Now, if you notice, sine of pi over 12, we did before, and with the sum and difference formula, we came up with square root of 6 minus square root of 2 over 4. And I suggest that's the sort of pattern you could memorize for the over 12s. Well, if I think of it as a half angle of pi over 6, now it becomes plus or minus the square root of 1 minus cosine pi over 6 all over 2. And again, we're in the first quadrant, both for pi over 6 and for pi over 12, so that's positive. So we're going to get positive square root of 1 minus cosine pi over 6 is square root of 3 over 2, all over 2. Multiply by 2 over 2 inside there. And we get the square root of 2 minus the square root of 3 all over 4. So I'm getting the square root of 2 minus the square root of 3 all over 4. Hold it. See, I'd have to accept that answer too. Let's get these out on the calculator quickly and see what we come up with for both. Okay, for the old way we used to do it, I'm getting a calculated answer of 0.2588 about. With the new way, I detect my error. The square root of 4, this should be a 2 here. And that's also about 0.2588. Now that's not a proof, but you can see why. If I said square root of 6 minus square root of 2 over 4 equal to the square root of 2 minus the square root of 3 all over 2, and let's cross multiply and maybe square both sides. 2 times square root of 6 minus square root of 2 equals 4 times square root of 2 minus square root of 3. Square both sides, so we get 4 times 6 minus 2 square root of 6 square root of 2 plus 2 equals 16 times 2 minus root 3. So that's 24 minus square root of 2 in there, so that's 16 square roots of 3 plus 8. Alright, and this is 32 minus 16 root 3. And sure enough, we get 32 minus 16 root 3 on both sides. Now, don't worry about which one you chose. I will accept either one of those approaches. Okay, now, the half angle formula for the tangent. One way to do this is just kind of brute force. You take the formulas we just did for sine and cosine. You say the sine of the half angle is plus or minus the square root of 1 minus cosine alpha over 2. And the cosine is plus or minus the square root of 1 plus cosine alpha over 2. And you put that just in one big happy square root. It's still going to have that ambiguity of plus or minus square root of, the 2's will cancel out, then we get 1 minus cosine alpha over 1 plus cosine alpha. I find a crisper version of this is when you go back to unit circle. Here's our alpha, and here's alpha over 2, because we're inscribing this angle as an inscribed angle on this central angle of alpha, and it's exactly half. That's a theorem from geometry. And then from the unit circle approach, remember this vertical distance is the sine of alpha. Stop clicking that pen there. Sine of alpha. And this little wedge in here, this is the cosine of alpha, just from here to here. But if I look at this big triangle now, tangent of alpha over 2 equals opposite over adjacent. And the opposite side is sine of alpha, and the adjacent side is this cosine alpha plus this distance. What's this? It's 1. It's the unit circle. Over 1 plus cosine alpha. Isn't that a nice, cleaner formula? Yeah. I left all this work to work it out. Anyway, if I look at the green triangle now, it's a little trickier because this is alpha over 2. This is a right triangle, so we got the complement of alpha over 2 over here over 2. So up in this little wedge up here, this is alpha over 2. So in the green triangle, the tangent of alpha over 2 equals opposite over adjacent again. Now this changed a little bit. This side is still sine of alpha, and this is cosine of alpha. And if the whole thing is 1, this is 1 minus cosine alpha right here. So we get 1 minus cosine alpha for the opposite side over the adjacent side sine of alpha. Here's another nice version of that. Okay? So 2 forms for, actually 3 altogether. This one. Let's put them together here. So tan of alpha over 2 equals sine alpha over 1 plus cosine alpha. Or it equals 1 minus cosine alpha equals sine alpha. Notice when you set these two equal and you cross multiply, you get that sine cosine Pythagorean relationship. Now a few class exercise 1 word problems. Here we go, 2 sine 3 alpha cosine 3 alpha. A lot of kids mistakenly start expanding this all out. It says simplify, and sometimes simplify means get into one trig function. So if we let's do a substitution, let beta equal 3 alpha. And so basically you have 2 sine beta cosine beta, which is the expansion for the sine of 2 beta. Now do your unsubstituting. Beta was 3 alpha. So this thing basically is the sine of 6 alpha. That is considered more simple. Now, admittedly, in the other problem, if someone said expand out to leave everything in terms of trig functions of just alpha, then you would have quite a job there for you, expanding that all out. Now, let's wrap up now with an identity. Prove this identity, 1 plus sine alpha, a minus cosine 2a all over cosine a plus sine 2a equals tan a. It must simplify, and this is not the side to work on. I mean, you could say sine a over cosine a, but you still don't have anything close to that over here. The issue is this is in a, so this other side, that is both a and 2a, we've got to get rid of these 2a's. Now, I've got a lot of choices on cosine 2a. Let's start on the bottom, actually, and say, well, we don't have a choice on what sine 2a is. That's just 2 sine a cosine a. And then you go, aha, there's a cosine a in common there. So that leaves 1 plus 2 sine a. So there's hope that this thing on the top perhaps can factor. Well, it's 3 terms, and this is 2 terms. To get rid of one of these terms, we want to pick the thing that's going to get rid of this 1. And we want to pick the 1 minus 2 sine squared a1, because that will cancel out the 1's. If we go 1 plus sine a, and then replace all of cosine 2a with 1 minus 2 sine squared a, the 1's will cancel out. We'll get 1 plus sine a plus negative 1 plus 2 sine squared a. Oh, this is looking good. The 1's cancel out. We get sine a plus 2 sine squared a all over cosine a times 1 plus 2 sine a. Now remember, this other side, we can start working on this as well. This is sine of a over cosine of a. So you can see we are so close. Sine of a over cosine of a. Got the cosine a ready to go there. Just need to factor out a sine of a. Leave behind 1 plus 2 sine a all over cosine of a times 1 plus 2 sine of a. Oh, très magnifique. Look at that. The 1 plus 2 sine a's cancel out. Whoosh, whoosh. And we get the sine of a over the cosine of a equals the sine of a over the cosine of a. Sorry, I did all the wrong slashing on that. Whoosh. Okay. All right. Flange out.